Hey guys, I have your notes for 6 days, 2 and 3. So we're going to get through some of the examples today, and I'll kind of tell you how that relates in your homework, and then we'll do the rest of the examples. I'll do the rest of the examples in the next video. So we're going to get started pretty heavily into related rates. This is one of my favorite calculus topics. The math involved, like the algebra steps, the calculus steps, they're not that bad. They're not like some of the optimization problems that you were doing earlier where it took a whole lot of work to get to your answer. This is more of a let's use your brain to get it from like real world problem to mathy where we can work it out on a piece of paper. So the first two examples in your notes. One is a spherical balloon being inflated. We're going to look at how different parts of that balloon change according to time. And the second one is about a ladder leaning up against a wall, and the bottom of the ladder starts sliding out from the wall. If you're on that ladder, you'd be panicking. So those are the two situations. I have something pulled up here. Let me switch computers. I have this really cool program that lets us watch. Maybe? There we go. Lets us watch how things are changing. So you can ignore all of the information. You can ignore all of the numbers on the paper. I just want you to watch the balloon being inflated, okay? Let's focus on that. All right, so you're watching a balloon being inflated. So the problem that this demonstrates doesn't match the problem in our notes. What they do have in common, though, is air is being pumped into this balloon at a constant rate. So the volume is changing consistently. So the volume may be changing consistently, but I think the radius of the balloon changes at a different rate depending on how much volume is in there. All right, so the volume is changing at a consistent rate. The radius, I believe, let me think about this. Yeah, look, at the very beginning, did you see how quickly that balloon grows in size? And now the growth seems to be slowing down. So when it starts, the radius grows really quickly. But as the volume gets bigger and bigger and bigger, the radius growth becomes slower and slower and slower. Okay, so hopefully that visual will help us get through the first problem in your notes. Now, the second problem in your notes is about a ladder leaning up against a wall. I have a picture for that one too. Again, all of this information on this page, it doesn't match the problem in your notes. I just want you to watch this ladder being pulled away from the wall. So suppose you're on this ladder, you're working to get to the top of the wall, or I don't know, something like that, and one of your devious friends comes by. They're like, oh look, he's on the ladder. Watch this. And grabs the base of the ladder and starts pulling the base of the ladder away at a constant rate, okay? They don't jerk it back and then slowly. They're not slow, and then jerks it. Just consistently pulling it back, letting you panic the whole time, right? So what you're going to see, first of all, the length of the ladder doesn't change. The second thing you're going to see, the distance from the base of the ladder to the bottom of the wall changes, because you've got some jerk that's pulling the base of the ladder out, right? So this length is going to be increasing at a constant rate. They are just pulling it back slowly at a constant rate. What's going to happen is the top of the ladder is going to start falling down the wall. Watch it. see what happened? Watch it again. Let's get it started. Pull out a consistent rate. Consistent, 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 consistent. We'll watch the top of the ladder. The farther out the base of the ladder gets, the faster it slides down the wall. See? Slowly, 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 faster, 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 faster. So here's what's going on. The bigger this length becomes, the faster this rate changes, right? The height of the ladder is going to change and change and change and change. The rate of change for the height of the ladder is slow at first, faster at the end. The rate of change of the distance to the wall is consistent. It's just a constant rate. Okay, so let's switch modes here. Let's go back. There we go. Give it a minute. There we go. Ready? Pick a color. We are going to start taking wordy to mathy. So we got air being pumped into a spherical balloon. Okay. The volume increases at a rate of 100. Volume, rate of change, 100. So I'm going to write dV dt equals 100. Switch colors. How fast? How fast? Find. How fast is the radius increasing? So that's asking for a rate. How fast is the radius changing? Find dr dt. At the moment, the diameter is 50. Now, if you think back to the image of the sphere increasing. So the volume, this is similar. The volume is being pumped in at a constant rate. The volume is changing at a rate of 100. The radius, however, do you remember watching it? How the radius grew really fast at first? And then the bigger the balloon got, the slower the growth became. So what's going to happen is we're going to find, in fact, let me keep talking about the radius. So when the diameter is 50, y'all will agree with me that that implies when the radius is 25, right? I don't want to talk about diameter. I want to talk about radius. So find the rate at which the radius was changing. Well, it depends, right? The rate at which the radius is changing depends on how big the balloon is. Because at the beginning, the radius was changing really fast. This would be a big number. But toward the end, when it got bigger and bigger and bigger, it was growing more slowly. The radius was. So this depends on when we want to look at it. So here's what's happening. We're picturing this balloon inflated, 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 and you're watching, and the instant the radius is 25, you're like, stop! How fast was the radius changing? Right then. So we're like freezing time when the radius is 25. Stop. How fast was it growing right at that moment? I bet it's different at this moment than it would be when the radius was like 2. This number that we're going to find would be different when the radius is at 2 versus when the radius is at 25. Okay, so that's what we're trying to do. We've gotten everything out of the problem. We've taken wordy to mathy, and now we've got all these rates. We need an original equation that we can do a derivative on. And it's basically telling you what kind of equation to use because you've got volume information right here. So we're going to do a volume equation. And this is a sphere, so you should know this because you memorized it yesterday. Volume of a sphere, I wish you were out there for me to call on you. Dang it. 4/3 pi r cubed. That's the original equation. We're going to do a derivative on that. Here we go. Oh, wait, before we do a derivative. Look at all these rates that you wrote. Change of volume with respect to time. Change of radius with respect to time. Guess what our variable is? It's time. V is obviously some messy function. R is messy function. We don't know what it is. We don't care what it is, but I can guarantee you R is changing based on seconds that go by. So here I go. I'm going to do the derivative of V is dv dt equals, I'm going to power rule it at first, lower it, chain rule it. Now, look at what we got. There's dv dt. I like it. I've got that information. There is a 4 and a pi and an r. Ooh, I have an r. I like it. And I have a dr dt. No, I'm finding dr dt. So let's plug in what we know. This is 100. Plugged in what I know. And if I were trying to do this problem without a calculator, which is completely reasonable to do without a calculator, I would not square this because I know that in order to solve for dr dt, I'm going to have to take 100 and I'm going to have to divide it by this, this, and this. So watch. Dr dt is equal to the original 100 divided by a 4 and a pi and a 25 and a 25, right? Yep. A 100 and a 4 and a 25 can cancel. And I can say that dr dt, if I don't have a calculator, I can say that is 1 over 25 pi. And you know what? Just for fun, let's throw units on there. Let's see. What are my units that I have? Okay, so I got volume is cubic centimeters per second. So my length measurement is centimeters. My time measurement is seconds. Radius. Radius is a single length measurement. It's not area, so it wouldn't be square units. It's not volume, it wouldn't be cubic units. It's just linear units. So this is my answer, and my units are centimeters, plain centimeters per second. Let's do the next one. This is the ladder leaning against a wall, so let's get a picture going. Okay, not a good ladder, but you get the picture. Ladder leaning against the wall. The ladder is 10 feet long. All right, well, ladder is 10 feet long. I'll put a 10 there. That is not going to change. Now, you can see that we've got like a right triangle set up. It's talking about the bottom of the ladder and this length right here. It's talking about the height of the ladder and this length right here. So I'm going to throw some variables on there. That'll help us go from wordy to mathy. So down across the bottom, I will throw an X down there, and I'll put a Y up there. So now that I have variables assigned, I can go back up. The bottom of the ladder, okay, the bottom of the ladder is sliding away from the wall at a rate of 1. So somebody is pulling the ladder out, constant rate of 1. Pulling slowly, pulling slowly, pulling slowly. So I can say that this length is changing at a rate of 1. So I'm going to write dx dt is equal to 1. How fast? Find. Is the top of the ladder sliding down the wall? How fast is this sliding down the wall? Well, when this slides down the wall, the height of the ladder changes. So that red phrase is telling me how the y measurement is changing. At the moment, at the exact moment, x is 6. At the exact moment, it's 6 feet away. Because remember, we said the farther away this gets, the faster this slides down the wall. So dy dt is changing. dy dt is slow at first. dy dt is fast at the end. We want to find it. How fast was this sliding down? How scary was it for this person on this ladder when this was 6 feet away? Right? I bet when it was 1 or 2 feet away from the wall, there wasn't that much panic going on for the guy on the ladder. But the farther away it gets, the faster it's sliding down the wall, and you're like, oh crap. All right, so we've got all this information. We need an equation. We need an equation involving an x and a y so that we can do a derivative on it. And I think many of you know what our equation is supposed to look like. So I'm going to use Pythagorean theorem, and I'm going to go x squared plus y squared equals, now for just a minute, I'm going to call this L for ladder. Okay? I know. You're like, but there's a 10 there. I know. I want to warn you about something. Before you do a derivative, you are not allowed to plug in numbers if something is changing. Let me explain that. Is this, in my problem, is this length changing? Yes, it is. I'm not allowed to plug in a number before I do a derivative. Because if I sub in a number for x, that is locked in, and I'm saying that this length isn't changing. Wrong. This length is definitely changing. I'm not allowed to sub in a number before I do a derivative. Is this length changing? Oh, heck yeah, it's changing. I'm not allowed to sub in any numbers for y before I do a derivative. If I did, it locks that value in, and I'm saying that it's going to stay that way throughout my entire problem. It's not true. It's changing. Is this length changing? The ladder is consistently 10 throughout the entire problem. You are allowed to put a 10 there. Now we're going to do our derivative. Remember, x depends on time, y depends on time. They're both messy. Whenever we encounter them, when we're doing our derivative, we have to use the chain rule. Here we go. I got 2x times dx dt. Chain ruled it. Plus 2y dy dt. Chain ruled it. Equals, don't mess this part up, derivative of a constant. This equation is all about change. My original equation If I sub numbers into this original equation, this is a moment in time. When x is a certain measurement and y is a certain measurement and the ladder is 10, this is a particular moment in time. This equation is all about change and how my x is changing and how my y is changing. It's all about change. You are allowed to sub in numbers to this equation at this point. Okay, so let's figure out what we can sub in. We've got, well, the 2 is going to stay a 2. And dx dt, do we have that? Ooh, we do have that. I got that. Do I have an x? Yes, I do have an x. It said when at the moment that x is 6, so I'll put that in. All right. So 2, x is 6, 1, plus 2 times y. Oh, I don't have a y. Dy dt is what I'm trying to find. This is what I'm trying to find. I need a number here. I'm only allowed to have one unknown in my equation. I need a number here. And you can do a number here. Because remember, the ladder is, we're pulling the ladder away, right? So what's happening is the ladder stays 10 feet long. We're pulling the ladder away. Somebody's counting or watching this length. When this length gets to be 6, somebody goes, stop. How fast was this changing? That's what we're trying to find. Well, when we stopped the ladder at 6 feet, how high up was it? So most of you know, just off the top of your head, hey, that's a Pythagorean triple. If you don't have that memorized, you can do y squared plus 6 squared equals 10 squared. Turns out at that moment, y was 8. At that moment, y was 8. Okay, so if I subtract 12 and divide by 16, I get negative 3/4. And it's kind of weird because it's a negative. Let's talk about that. I got a negative for my rate of change of y. Here's why it was negative. This length was decreasing. This length was increasing. This rate is positive. This rate is negative because y is decreasing, okay? So, caution, caution. Negative 3/4 is not my answer to the problem. It's the answer to my equation, definitely. Now, ready? Let's answer the question. How fast was the top of the ladder sliding down the wall? Do you see how it already mentions that it's decreasing? So if it mentions that it's decreasing, if you throw a negative in, that's a double negative and it changes to positive. So you got to be careful about the way you word it. How fast was it sliding down the wall? At a rate of 3/4. And then throw units on there. It's a linear measurement, so it's going to be, I think it's feet. Yeah, feet per second. 3/4 feet per second. That's my answer. I did not use the negative in my answer. Now, let me just give you an example of how it would sound if you were supposed to use the negative. What if it had said, how fast is the height of the ladder changing? Those words mention nothing negative in them. How fast is the height of the ladder changing? Then my answer would be negative 3/4. But since it's already mentioning that it's decreasing, I'm not going to throw in the negative. Okay, let me show you the next two problems. I think we've got a cone and an intersection. Yes. We've got a cone and an intersection. Okay, so here's the cone, right? And it's like one of those little water cups, and we're going to fill the cone up with water. Here I go. Fill. So a couple things I notice. Yes. The one thing that this situation and our notes have in common is water is being filled into the cone at a constant rate. So my volume, my rate of change of volume is a constant rate. In this problem, it's 2 cubic centimeters per minute. Okay. So the volume is what's changing at a constant rate. Notice at the very beginning, look how fast the height grows, the height of the water. It shoots up really fast. And then as the cone gets fuller, more full and more full, the height seems to slow down a little bit. All right, so the radius is changing at its own rate. The height is changing at its own rate, and the volume is changing at its own rate. dV dt, dr dt, dH dt. Okay? Keep that in mind. And while I'm here, let me go ahead and show you the next one, which is the, here we go. Here we go. We got a truck and a car approaching an intersection. Let's see what happens. Oh no, what's going to happen? Phew. Looks like they made it. Come on, start over. Jeez. There we go. Notice that the distance from the car to the intersection is changing. This is changing. This is the distance between the two vehicles. It's changing. So as they were approaching each other, the distance between them became smaller and smaller and smaller and smaller. This is still a right triangle problem like our ladder was. The only difference is we got a right triangle going on. Pythagorean theorem, the only difference is now this is a changing measurement. Unlike our ladder, which was consistently 10, this is a changing measurement. Okay, so take those visuals in your brain and let's work these out in the notes. So I want you to draw, for example D, I want you to draw an inverted cone. Doesn't have to be beautiful. Inverted cone. And when it's empty, the radius is 2 and the height is 4. Four, 2. Okay, so you can see that we got an empty cone here. Height is 4, radius is 2. Do you see the right triangle that's formed with the radius, the height, and the slant piece? It's a right triangle. Look at what happens when I fill it with water. Okay, check out the right triangle that I made of water. The height of the water is not 4. The radius of the water is not 4. Sorry, it's not 2. The height of the water is not 4. The radius of the water is not 2. But remember that original triangle that we had? Look at this smaller version of a triangle. Here's what's cool about this triangle and this triangle. They share the same angle. They're similar. Okay? So wherever the water level is, I'm guaranteed that the radius of my water level and the height of my water level still maintain a relationship of 2 to 4 or 1/2. The whole time it's filling, the radius of the water that's in there and the height of the water that's in there will always have a relationship of 1 to 2, 2 to 4, whatever. So I can come over here and say that my radius is always going to be 1/2 the height. Or, in other words, another way to phrase it, my height is always twice my radius. This is an important relationship that's going to carry through during the whole filling of the cone. Okay, now that we've established that, let's keep going wordy to mathy. Water is being pumped in, okay. Water is being pumped in at a rate of, now notice it never mentioned volume. I know that what it means is the volume is changing. What if you don't recognize that? What if you're so overwhelmed with calculus, you're like, how do you know it's volume? Here's a good clue on how I know that's a volume rate. Look at the units it gave me. Volume per minute. Cubic meters, that is a volume measurement. So if you don't pick up on the fact just in the phrase that it's what type of measurement it is, always refer to the units, and that'll help clue you in. So it's a rate, so I'm going to write dV dt equals 2. Okay, find the rate at which the height dH dt, can you all pull that out of there? Find the rate at which the water level, the height, when, what's a color that I haven't used already? When the height is 3. Okay. That's it. I've got wordy to mathy. I've got it all done. So we got volume, we've got dH/dt, we've got H. So we're going to need a volume equation. Let's get us a volume of a cone. Volume of a cone is 1/3 pi r squared h. Now, if you recall, in the last set of notes, we did a derivative on this, and we had to product rule it, right? So we had to do product rule, and we had to use a dr dt, and we had to product rule, and we had to use a dH dt. Okay, so if you can kind of like look at your equation before you do a derivative on it, and just make sure that you have everything that you're going to need to plug in. So like, if I do a derivative on this, I'm going to have dV dt over here. Is that okay? Yeah, it's okay. I'm going to have a dr dt in my derivative. I'm going to have a dH dt in my derivative. Is all that okay? It's not. I have no R information at all to plug in. I don't have a radius to plug in. I don't have a rate of the radius to plug in. So we've got a problem. We can't do a derivative yet because R is like an extra piece I need to get rid of. R is an extra piece I need to get rid of. I can keep H. Look at all this information I've got about H. I need to get rid of the R. How am I going to get rid of the R? Go to the relationship over here that we established between the radius and the height. You will always have a relationship something like this with your radius and your height of a cone. So what I want to do is I want to keep the H. I want to get rid of the R. Let's plug that one in. Haven't done a derivative yet. Not doing a derivative yet. Pi R squared H. And now, just because I know I'm getting ready to square it and do all that stuff, I just wrote it as H over 2. I thought it would be easier. Okay? Some of you are like, okay, let's go. Let's do a derivative. No. This is so complicated. If you try to do a derivative on that, more than likely you're going to mess it up. Simplify it before you do a derivative. So, I've got V equals, let's see, that ends up being H cubed. So I've got pi over 12 H cubed. Is that right? That becomes a 4 on the bottom. That's a 3. That's a 12. I stuck my pi up there just because that's all a constant. And then my H squared times H ends up being H cubed. Look how much easier of a derivative this is going to be than that would be. Let's go. Let's do it. So I've got dv dt equals pi over 4 H squared, chain rule it. Now, this is good. This is what we're trying to find. This we have. We can plug it in. And this we have. We can plug it in. If I had a calculator, I could figure the decimal version, but there's no need. I mean, it worked out so nicely. Find the rate at which the water level is rising. So if I put units on that, I would have 8 over 9 pi height. Height, that's linear, so it's going to be meters per minute. Here we go. All right, now I am at the 39-minute mark on this video, but I'm going to go ahead and do this last problem, still in this video. If you're tired of watching, pause it, come back to it later. But that only leaves one more for the next video. But yeah, that's what I want to do. So, bear with me. We've got 2 cars traveling toward an intersection, and one's going west and one's going north. So I got one driving west, and I've got one driving north. So I want, when I graph it, I really want largely like to look at quadrant 3. I want to give them room to, move. So let's go car A is traveling west. So I'm going to make car A go this way. My fantastic car that I'm drawing, that's car A, and he's going this way. And car B is going north. So he's going to go this way. This is going to be car B. Fantastic car going this way. Approaching an intersection. Now, car A, car B. So I've drawn kind of what they're doing. Now also I can go ahead and write their rates. So I can write car A's rate. Remember, I'm going from wordy to mathy. I can write out their rate. The thing is, before I write out its rate, I need a variable on its length. I mean, you can call it whatever you want. I think I'm going to call that one X and that one Y, just because horizontal, vertical, you know? So now, let's take wordy to mathy. So now I can say that this length is changing at this rate. So dx dt is it 50? Is that right? This length is changing at this rate. This car is going 50 miles per hour, so x is changing at that rate. Well, here's the thing. X is decreasing. So its rate of change really needs to be negative. And let's do car B. Car B's rate is this. Car B's rate is this. Well, car B's length, distance from the intersection, is decreasing. So I can say dy dt is negative 60. At what rate find? At what rate are the cars approaching each other? So the distance from car A to car B. I think I'll call that, I don't know, Z. Y'all don't like Z. Looks like a 2. Let's call it D for distance. How's that? Find the rate. So it's not saying find how far apart they are. Find how fast this green segment is changing. Find the derivative of d with respect to t. At the exact moment, it's a lot of information in the problem, when car A is 0.3 miles away, and car B is 4 miles away. I think I've got it all. I got car A, I got their rate, I got car B, I got their rate, they're headed for the intersection. At what rate, find how the cars are approaching each other, so the distance between the cars. When, that's that, and that's that. So they're going, right? We're looking at how fast this is changing. They're going, and when he gets 0.3 miles away and he gets 0.4 miles away, we're like, stop, freeze. How fast was this changing right then? I'm going to start with Pythagorean theorem. Be careful, you don't have anything to plug in yet. This is a changing length, this is a changing length, this is a changing length. By the way, I should have said that up there. When I made a volume equation, volume is changing, radius is changing, height is changing. They're all changing. You may not plug in a constant for any of these until you've done your derivative. Okay, let's keep going. We're almost there. Here I go. Derivative, I'm going to go 2 times x times chain rule plus 2 times y, use chain rule. 2 times d, use chain rule. I know that x at that moment, I can plug in 0.3. I can plug in dx dt, which is negative 50. Two times y. At that moment, y was 0.4. dy dt was negative 60. This is what we're trying to find. So I got numbers everywhere. I got numbers everywhere except here. Oh, man. At the moment that this is 0.3 and this is 0.4, what was this? Well, they gave them to you as decimals, but it's okay. It's still a Pythagorean triple. So if you don't know it, you can always figure it out. 0.3 squared plus 0.4 squared equals d squared. It's 0.5. 0.5. Okay, so what ends up happening is I get the distance is changing at a rate. This becomes negative 78. Okay, so I solved it, blah, blah, blah. I got negative 78. Is that the answer to the question? It's a negative. Be careful. Is that the answer to the question? At what rate are the cars approaching each other? So does the way this is phrased already lead you to believe that that distance is decreasing? It does. At what rate are they approaching each other? So I'm going to leave off the negative when I give my final answer. 78. Is it miles per hour? It is miles per hour. When would I leave the negative on? If it had said, at what rate is the distance between the cars changing? So if the question kind of leaves it open to where, well, they could be growing farther apart or they could be growing closer together. If it kind of leaves it wide open, you would have to use the negative. Or in your answer, say they are approaching at a rate of 78. Okay, the negative's got to be there somewhere, whether it's in the way that it's asked or whether it's in your answer. It's got to be there somewhere. All right. Whew, that was a long one. I'm sorry. The next video that you watch will be super short. We only have one problem to do.